This video is another in the series for Math 1133 for UTSA. Today we're going to be talking about 13.7, differential equations. I'm showing you this, which looks a little odd because I'm reusing some videos I made before, and they started with this sort of header. In that course, we were using a module-based approach, and Module 10 covered differential equations. For us, we don't need to call it that, but I didn't want to just show up in mid-video and you have no idea why it's called that. So basically, whenever you see Module 10 in the video, just ignore that. Don't worry about that. That's just a leftover because I'm recycling a video. Anyway, basically, a differential equation is an equation that has a derivative in it. You can see this example here. We have f prime of x equals 2x minus 1, right? We're going to solve this equation, and it's basically just an initial value problem. We've done this before. Now, there's two ways to approach this. So first, we're going to solve this as an initial value problem, which is the most basic type of differential equation. Then after that, we'll work the problem again, but we'll treat it with a different technique, which applies to what are called separable differential equations, which is the category that we're going to be dealing with the most. There are other types that are beyond the scope of this course. We're just dealing with the two most basic types, the initial value problem and then the separable differential equation. Also, at the beginning of each example, I'll say something like, in this video, we're going to blah, blah, blah. That's because originally each example was a separate video. I've just edited them together for this video. Okay, so in this video, we're going to work this example of an initial value problem with an eye towards redoing it as a differential equation. And you'll get, from that comparison, hopefully you'll get what it means to have a differential equation. So this is something that we've really done before. I guess this was the very end of, what would that be, Module 7, I think? I'm not quite sure now that I think about it. But, so this is an earlier module or earlier chapter, and where we dealt with this. And basically, when you're given a derivative function and what's called an initial value, f of 0 was 4, right? Here's the derivative, and here is some value of it. Well, we can work backwards through an antiderivative to find the original function. So f of x is going to be the antiderivative of f prime of x, 2x minus 1. When you find an antiderivative, or an indefinite integral, we're going to use the power rule. So the antiderivative, or rather an antiderivative of 2x will be x squared. This one is chosen to be relatively simple. And an antiderivative of 1 would just be x, so minus x. And then you always put plus c at the end of your antiderivative, because it's kind of like there's a sneaky plus 0 hiding out at the end of the function, because when you find the derivative of a number, you get 0. So maybe there was a number there all along. Maybe it was 7 or 8 or 12. We don't know. But this is called an initial value problem because we're given when you input 0 into the original function, you should get 4 as a result. So that means that since this is my function, f of x equals x squared minus x plus c, if I plug in 0 here, f of 0 would be 4, right? And then we'll say, okay, well, x is 0, so this is 0, it's plus c. So that means that c, the number c, should be 4. And we can think of it if we want as, oh, it was 4 all along, but we don't know that. This c is 4, but we don't know that until we plug numbers in and check. So that means that my real solution is f of x equals x squared minus x plus 4. Okay, so this is the way we solve the initial value problem version of this example. One thing that will lead into the next example is that this solution is often called the general solution. This is also why this is called the general antiderivative. This is the general solution to the initial value problem. Make sure I write that a little bit more neatly. Once we find out what c is, this is called a particular solution. I guess you could call it also specific solution, but the term particular is what's used, particular solution. So there you go. That is something we've already done, but it's just a rehash of how do you solve this problem with an initial value approach. Okay, so in this video, we're going to rework essentially the previous example using a different approach. So you notice we still have 2x minus 1, but I'm not calling this f prime of x. I'm calling this dy dx. That's just a notational difference, and we'll talk a little bit more about that in a second. And instead of writing f of 0 equals 4, I'll just say 0, comma 4. Like this is an xy pair when x is 0, y is 4, which is essentially the same as saying f of 0 equals 4. So the technique for doing this is something that has a lot of technical details in it. And rather than going through all the details, I'm just going to show you here's the procedure, and I'll talk a little bit about the details afterward. So what I'm going to do is when we're approaching this problem as a differential equation, specifically a separable differential equation, let's call it that right now, separable. So that is not how you spell separable. Separable differential equation. What that means is we're able to separate the variables. All of the x's can be on one side and all of the y's can be on the other side. In particular, this dx, this is similar to, well, this is the differential that we dealt with when we did integration by substitution. So we had to change dx into, for example, du or dv, that kind of thing. So this is the differential. And we might talk a little bit about that and how it relates to delta x again after we work this example out. Just to recap some of the motivation for why we can move things the way we move them. Right now, dy dx, this is the derivative. This is like saying f prime of x. This does not mean we have a fraction, but we're going to think of it as being one anyway, in short, because that gets the job done. We'll talk about the technical details a little bit in a minute. So I'm just going to write, well, this is going to be dy equals 2x minus 1 dx. Okay, I'm thinking of it like I'm multiplying dx on both sides. There's technical problems with doing that, but let's not worry about those right now. Let's just try to get the problem completed. So now I can integrate both sides. Okay. Now on the right, this is just an antiderivative. This is something we did in the previous example. That shouldn't be too hard. The left, this is very new. This is maybe not so clear. What I want you to think about is, think of dy as being a variable like any other, and it has a coefficient, and if there's nothing written there, you put a 1 as the coefficient. So this is really the antiderivative of 1 dy. Okay, not just the antiderivative of dy, because that's a little cryptic. What's between the two symbols, right? The integral symbol and the dy. Let's go ahead and do the right-hand side first. This is what we've already done. So we get x squared minus x plus c, right? The antiderivative of 1 is x when dx is the differential at work in the antiderivative, in the integral, right? Now over here, we're doing the antiderivative of 1, but on the left-hand side, the active variable is y, not x. So my antiderivative is not x, it's y, okay? The difference being entirely that, well, these are not the same differential. Basically, the differential is that little slice of the variable. When you integrate or accumulate little slices of a variable, you get the variable, okay? This is something we talked about a little bit when we talked about substitution. So this is essentially what I got in the previous example. And in fact, the right-hand side is identical to the previous example, no differences. The differential equations approach versus the initial value problem approach lies entirely on how you treat the left-hand side, which will become very important in a later example. For this one, I've chosen one specifically where the two approaches are essentially the same. You really don't need this approach for this problem, but I wanted to introduce the procedure with an easy problem, not a hard problem, of course. So now I need to figure out what c is, so I need to use my initial value whenever x is 0, y is 4, right? So if I put in 4 for y and 0 for x, the right-hand side, 0 minus 0 plus c, that's c, so c is 4. So that means that my particular solution is y equals x squared minus x plus 4. Again, this guy with the plus c is the general solution. And this guy here with the plus 4, this is the particular solution. And you can see if you go back and look at the previous example, this is the right-hand side is essentially identical. I mean, I wrote a plus c here. I made it slightly different, but it's the same thing, right? I wrote an additional step out, but it's the same thing. So the difference is in how you treat the left-hand side. And so I want to talk about what happened between these two steps a little bit. If we say that that y equals f of x, y is the output variable for some function, x is the input variable, then we have two basic, there are more than two, but in this course we have two basic forms of notation for the derivative. I can say dy dx. This means the derivative of the y variable with respect to the x variable. This equals f prime of x. This is the derivative of the function f with respect to the variable x, right? The difference is in notation, not in the content of what's happening. It's merely notation. So this is called the Lagrange notation, Lagrange prime notation. This is called the Leibniz notation. I sometimes call it the Leibniz fractional notation, or the Leibniz fraction-looking notation. It's literally not a fraction. There's no division here. It's just notation. However, the reason that this is used is because sometimes the derivative behaves like a fraction. Remember that the derivative is the limit of the difference quotient, right? So it's the limit of a fraction, so it has some behaviors of a fraction, which sounds really strange. Wait, there's a thing that behaves like a fraction sometimes? And the answer is, well, calculus is weird, so yes. So when you have a differential, you might remember back when we did substitution. If I wanted to do a substitution, I want to say, oh, well, u equals this function of x, and I'm going to replace dx with du. Well, we define the differential of a variable, of an output variable specifically, as the derivative of that function as a function of some input variable times the differential of the input variable. And the differential of the input is like a small slice of the input variable. It's a lot like delta x. It's not the same thing. There are technical details we're going to skip, but it's similar. So in this context of a differential where we have dy on its own, dy equals this product f prime of x times dx, now I can divide, because right here this is a product, this f prime of x times dx, it's a product. I can divide dx rather, on both sides, okay, and get rid of the dx on the right, and so I have dy dx equals f prime of x. And in this context, this is a genuine fraction because of how it was formed. Because I'm saying, well, I have this differential dy, and it equals this thing that we've talked about previously. I can divide in an equation, divide by whatever I want. As long as I'm not dividing by 0, I can divide whatever I want. However, up here, with just the Leibniz notation, this is not a fraction. You might say, but they look identical. What is the difference between here and here? And the answer is, well, there's a bunch of technical differences that we're overlooking. This is why over here, I say, let's not worry about why the dx is moving. Let's just put it over there. Let's not worry about, is this a fraction? Is it not? Are we multiplying? Don't worry about it. Just move it, okay? And what we're doing is we're glossing over details, which for the kinds of problems we're going to do aren't super important. We're not going to do problems complicated enough where those details become necessary to really work out what's happening. We could ignore all this explanation and just follow the procedure and we'll get the right answer, okay? For the problems we're doing in this class, we don't need all the details. If you wanted to be an engineer and you wanted to, design computer chips, or you wanted to design more efficient solar panels, well then, yes, now you need all these details because the details in the calculations are important at that point, but for this course we don't. Anyway, that's our first example of a separable differential equation, and in the next few videos we'll do some more. Okay, in this video, we will do another example of a separable differential equation. This one, as with the previous one, will be relatively simple. We'll get to the more complicated one soon enough, though. So, here's our equation, dy dx minus x equals x squared. Okay, so any equation where there's a derivative, that's a differential equation. And then, of course, this one we have an initial value 1, 2, meaning that when x is 1, y is 2. Okay. For now, notice the similarities between this example and the previous example. For now, y only appears in one place. That's what makes it easier. We'll get examples soon enough that have y in more than one place, but for now, we'll go with this. So the first step here is I want to get all the y's on one side and all the x's on the other side. So this x has got to move, and this x has got to move. And what order do we move them in? Do we move the dx first, or do we move the x first? Well, as I said before, again, this is technically not quite right, but let's not worry about technical details. I want to think a little bit about this just being order of operations. If I'm going to multiply by dx, well, that's more complicated than adding x first. I really want to move this guy first. I just add x to both sides, and then worry about the dx afterward. Kind of like if I had something like, I don't know, y over 7 minus 3, or minus 7 rather, equals, I don't know, 49, right? If x was 7, in fact. I could multiply 7 on both sides, but that would modify this one and this one and this one, all three. I'd have to modify all three elements if I multiplied by 7, right? Whereas if I add 7, oops, I only have to modify these two. This guy is untouched if I add 7. So when you're manipulating these separable differential equations, although, as I said before, this is not a fraction, but let's not go back down that rabbit hole, but it's not a fraction, so I still am going to think about order of operations. Okay, I'm still going to try to follow those rules because they get the job done. Okay, so I'm going to add x to both sides. So I have dy dx equals x squared plus x, or if I want x plus x squared, the order doesn't matter. And then next, I'm going to move the dx to the other side. And as I said in the previous example, we're not going to worry about y. Why is it moving? Are we multiplying? Let's just not worry about that. Let's just move it, okay? Now, I do need parentheses because we, at this point, are literally multiplying. But in this transition step, let's not worry too much about what happens, because to really get down the details of what's happening and why would take a lot of time and be very tedious. So let's not do that. Let's just follow the procedure. We'll get the job done. Okay. On the left-hand side, I have just dy by itself. Dy is a variable. It's an output variable, output of some function. So I want to have a coefficient, and I'm going to put a 1 in front. I don't have to write the 1, but it might make the next step a little bit more clear. Now I'm going to integrate both sides. And in the previous example, we did the right-hand side first, but I don't see any reason we can't do the left-hand side first. So I want the antiderivative, or rather I should say an antiderivative, of 1, keeping in mind that y is the active variable. So if y is the active variable, what would you find the derivative of to get 1? Well, you can, of course, pause the video and think about it, but that would be y. The derivative of y with respect to y is 1. In other words, dy of y equals 1. This is something we've probably talked about already, talking about the chain rule, but it doesn't hurt to point it out here. Since we have two different antiderivatives at work, it doesn't hurt to point out, to remind you of how to find an antiderivative with respect to a variable that is not x. The right-hand side, we're just going to use the power rule. So I'll have 1/3 x to the third power plus 1/2 x squared. Let's see. There's something that I'm doing here that I also did, or in other words, didn't do in the previous example. You might wonder, how come I don't have a plus c on the left? The antiderivative should always have a plus c, so why don't I have one, right? Well, the reason for that is that if I were to have a plus c on the left, I would ultimately move it to the right anyway. So if I wanted to, I could do like this. I could say, okay, I have plus c and like plus k to make up a number, right? And then later on, I'll subtract k on both sides. So I'll have y equals some stuff plus c minus k. So I have a number that I don't know minus a number that I don't know. And this will be grouped together because they're both numbers. And they'll ultimately get replaced by something based upon the initial value. So having the c and k in both sides, they'll get combined later anyway, so I don't need them. So typically, we'll put the plus c on the right-hand side, and we won't worry about the left-hand side having a plus anything because it would ultimately go away anyway. That's basically the reason. So now I can go back and use my initial value, 1, 2, and x is 1, y is 2. This is the general solution. Okay, general solution. So when y is 2, x is 1. So I have a 2 equals, I guess that's 5/6. Oh, I didn't square that. It's not super important because 1 squared is 1 anyway. 1 cubed is 1. So I have 1/3 plus 1/2, which is 5/6. Plus c. If I subtract 5/6 on both sides, I'll get 7/6 equals c. Of course, we could be using a decimal here. But 5/6 is 0.866666, I believe, something like that. You round off to 0.86666667. You round it at some point, right? And there's really no need to do that. We just leave it as a fraction. Sometimes you want a decimal, sometimes you need a fraction. Or rather, sometimes you need a decimal, sometimes you don't, and a fraction is just fine. In the homework assignments, you might need to stick with fractions. The problem will tell you if you should be rounding or not. Anyway, that means that my particular solution is y equals 1/3 x cubed plus 1/2 x squared plus 7/6. Okay, so there's my particular solution to the differential equation. Okay, so that is that example. This one was relatively simple, like the previous ones. In the next example, we'll start getting, well, maybe the one after that, I haven't looked ahead just yet, but soon we'll get to ones that are a little bit more complicated. Okay, so this is another example of a separable differential equation, and this is the first one where it starts to get a little bit harder. It's quite different from an initial value problem, because this one is not given as a function of x. dy dx equals y. Previously, we only had y in one position, and everything else was dx on bottom, of course, and then equals some function of x, 2x minus 1, or we had, like, I think dy dx minus x equals x squared, something like that. Now there are no other x's. There's a y instead. This makes it a fair bit different. So the overall procedure is the same. I want all the y's on one side. I want all the x's on the other side. So I'm first going to move the dx, as we typically were doing. dy equals y times dx. Okay. Now this y has to move. So I'm going to divide y on both sides. So 1 over y times dy equals dx. Okay. Now on the right, I don't have a number in front of the dx. I don't have an x. I don't have anything. So the default coefficient is 1. When nothing's written there, 1 is the coefficient. So I have 1 over y dy equals 1 dx. Okay. So now I can integrate both sides. And the right-hand side is probably the easiest, right? What is the antiderivative of 1 when x is the variable? Well, x. Plus c, of course. On the left, what is the antiderivative of 1 over y? And you might remember, if you're watching this, pause the video, think for a few seconds. What is the antiderivative of 1 over y? What would I start with and find the derivative to get y? Okay. And there's a good answer and a better answer. There's one that's almost correct, and of course, then there's one that's correct. Anyway, whether you paused or not, you might, if you did pause, you might have thought, oh, ln of y. There you go, that's it. The natural logarithm, because the derivative of ln of x, sorry, I'm trying to write this, here we go. The derivative of ln of x is, the derivative of ln of x is 1 over x. So the antiderivative of 1 over x is ln of x. So there you go. ln of y I should be writing, right? Well, you might recall when we talked about antiderivatives a while back, this is actually the ln of the absolute value of y. And that's fairly important because y can be negative. Remember, y is the derivative of whatever the function is. Well, the slope could be negative, maybe, right? And when we're finding the antiderivative of 1 over y, there's no reason that y can't be negative. 1 over negative 1/2, 1 over negative 1/8, right? Y could be negative. But when you have the natural logarithm, ln of a negative value is not defined. The domain of the natural logarithm would be 0 to infinity, not including 0. 0 is not a valid input. Negative numbers are not a valid input for a logarithm, any logarithm. So we have to use the absolute value. So now we need to try to solve this equation for y, and it's not so simple. There's several, this is why I said that this is our first example that's not so simple, because we get to this algebra part, and getting y by itself is not so easy. So there's more than one way to do this. I'm just going to go through the way that seems easiest to me. So I have this ln, and I want to move it. So I'm going to think about, well, there's two ways to think about this. One is this. If you have, say, ln of something equals something, so ln of a equals b, right? Well, I can just say, well, by definition of what ln is, referring back to what ln is defined to be, this means that a equals e to the b power. I just refer back, by definition, that's what ln means. It means that this ln, the natural logarithm function, is the inverse function for the exponential base e function. So if I have an ln on the left, I can just shove it to the right, it becomes an e.
as a base, exponential base. That's one way to think about it. Another way is to think, oh, well, I'm applying the base e exponential function to both sides, and ln and e cancel. It's effectively the same thing. I'm going to opt to go with that. It doesn't matter which way you think about it. There's more than one perfectly good way to write this out. So that means that the absolute value of y equals e to the x plus c power, okay? And there's a couple of ways to proceed from here. In particular, this could be rewritten to be different. I think we'll put that off until later, though. The next thing I want to think about is this. Is this. We have an absolute value. How do we deal with that? This means that y could be negative. You might think, oh, well, that means y equals plus or minus e to the x plus c. And that's a reasonable way to think about it. But the problem with that is plus minus means we don't have a function. How do we deal with this? Well, this is where we need to bring in our initial value. So we're thinking about our initial value. 0, 1 is our initial value. When x is 0, y is 1. When x is 0, y is 1. Okay. So y is positive. So 1 equals plus minus question mark e to the 0 plus c power. Well, 1 is positive, right? And e to whatever is always positive. An exponential function can't produce a negative result. So that means that we actually don't need that at all. Y is just e to the x plus c power. If our initial value had been different and we had something like, 0, -1, well, then we would keep the minus. But in this case, we don't. Again, I warned you this gets a little bit more complicated. So what this means is, for one thing, we don't have a minus here. It's y plus e to the x plus c power. But also, we can say, oh, well, that means 1 equals e to the c power. E to the c power is 1. Okay, that's going to help us a little bit. So bringing this down here with our newfound information about the plus minus situation, y equals e to the x plus c. And I need to use some properties of exponentials. When you have, where should I put it? I guess I'll put it over here. Right, okay. So when you have like 2 cubed times 2 to the 5th, right, that means 2 times 2 times 2, right? And then this guy means 2 times 2 times 2 times 2 times 2. So there's 3 of them and then 5 of them. That means there's 8 of them, right? 2 to the 8th power. I have 3 plus 5. And this is reversible. If you have a sum in your exponent, you can separate into a product. So that means that over here, these two guys can be two separate exponents multiplied together between the two. So this will be e to the x times e to the c. Okay? But that equals 1. E to the c is 1, so this is e to the x. So that's our solution. Y equals e to the x. So this is the solution. It's our particular solution. And this is why we're doing this example, because we've talked about this function quite a bit. Here's solution 2, dy dx equals y with the initial value 0, 1. Okay, this is what makes the base e exponential function special. It's the solution to this differential equation where the derivative is equal to the y coordinate at every point on the graph. That's why the derivative of e to the x is e to the x, because that's what y is, right? dx of e to the x equals e to the x. But that's what y is. That's the y coordinate, right? Y equals e to the x. So the derivative of the function is the y coordinate. That's what makes this function special. Anyway, so that was an example, which was a little bit harder, in part because we had to do more work at the beginning to get the variables separated, but then also we had a bunch of algebra to do. Okay, so some of our future examples will have both of those features. We'll have to do a little bit more work at the beginning before we do the antiderivatives. And then we might have some algebra work to do as well. Okay, here is our next example of a separable differential equation. And like the previous example, it requires a little bit more work at the beginning. and then we have maybe some algebra to do at the end. But this one I think will be a little bit easier overall. So our standard approach to start with is to get the dx to move. So I'm just going to throw the dx onto the other side. So dy equals 2x over y squared times dx, all right? And remember, my goal is to separate the variables, get all the y's on one side, all the x's on the other side. So this y squared needs to move. And I would encourage you to pause the video and think about, how am I going to move that y squared? And don't think too hard. You might, thinking about a couple of possibilities, you might, your first inclination might be correct. You might go, no, that's too easy. There's no way it's that. So go ahead and pause the video and think about it. Okay, whether you pause the video or not, we're back. I'm just going to multiply y squared on both sides. I have a fraction. I want to move the denominator, so I multiply y squared on both sides. If I can write y squared neatly, of course. So on the left, we'll have y squared dy equals 2x dx. Okay, so now I've separated my differential equation. I've separated the variables. Okay, so now I can integrate. On the left, which will be maybe slightly harder, in principle, this should not be any harder. We've been doing this exact problem for a while now. It's just the context is different. It might seem weird. We're used to mostly doing integrals with x as the variable, but now y is the variable, but all the same rules apply. So I just use the power rule. I have y squared. Okay, I'm doing the antiderivative with respect to y. The variables match. Power rule. So I'll increase that 2 to a 3 and then divide it. So I'm going to have 1/3 y cubed, or if I want, y cubed over 3. So 1/3 y cubed equals, so I can write a 3 neatly. That's pretty good. Equals, well, I want an antiderivative for 2x. I think every example we've done so far had this, or most of them did. So this will be x squared. So x squared plus c. And you might be wondering, what if I put the plus c on the left instead of the right? Would that work? And ultimately it would. I think the problems in my math lab, or if we're using WebWork, then in WebWork, whichever one it is, they would probably expect the plus C to go on the right if there's a problem like this, just because of the way that the software is written. It doesn't like to have it on the in quotes, wrong side. But really, in a technical mathematical sense, it doesn't matter which side you put it on. As we talked about in a previous example, really, it's kind of like there's on both sides, but when you move it over and you end up completing the problem, when you solve for y, essentially, they just sort of congeal into one, so you don't need to have both. It's sort of a shortcut to not put it on both sides because it's unnecessary at the end anyway. So I would like to solve for y. I want to have a function y equals some function of x. I would hope to, right? So there's a couple of ways to do this one. The order in which we do it is optional, and I think it's going to be slightly easier if we go ahead and find out what c is now. That'll make things a little bit easier for us. Our initial value was 0, 2. So when x is 0, y is 2. Okay, so 1/3 times 2 cubed equals 0 squared plus c. So that means that c is 8/3. Right? 2 cubed is 8 over 3. Okay, so 1/3 y cubed equals x squared plus 8/3. And I don't know about you, but I don't like having fractions like that. I have two fractions with a 3. I'm going to multiply both sides by 3, just because I don't like having fractions like that. I guess, well, you know what, also, just because we need to move this 3 anyway, I suppose. So no matter how you do it, you're going to need to do that anyway. So y cubed equals 3x squared plus 8. And then if the left side has a cube on it that's an odd exponent, I can just apply the cube root function to both sides. So y equals the cube root 3x squared plus 8. Okay. And when you have an odd exponent like this, you don't have to worry about pluses or minuses. If this was y squared equals something, well, then we would have to worry about that. But because this is odd, we don't have to. as a brief reminder, why is that? Well, when you square a negative number, it loses its negative, its negativity. And just looking at 9, if I say, oh, what did you square to get 9? Well, it could be 3, it could be -3. It's not, it's not clear which one it is. There's 2 ways to get 9 through squaring, right? So in a previous example, we had to deal with some plus minus issues. Because it was because of an absolute value, actually, in that case. But when you cube something, if I have -3 cubed, well, that's -27. You know that there's a negative there because 3 cubed is 27. So with an odd exponent, the minus is there when it's supposed to be, and it's not there when it's not supposed to be. Whereas with an even exponent, then it's a little squirrely. There's a plus or minus floating around. So for this one, we didn't have to deal with that. So our solution to the differential equation is y equals the cube root of 3x squared plus 8. Okay. Yeah, so that's that example. I think with this one, in previous examples we really were just solving an initial value problem. We didn't really have to use the separable separation of variables approach. This one, however, because we have y in the right hand side, y is part of the derivative formula. We're kind of stuck with using the separable variables approach, separating the variables. We're stuck with that because what else do you do with y? How do you find an antiderivative for 2x over y squared? By separating first. It's the only way to do it. So in previous examples, we were really just doing an antiderivative. And the left-hand side was, you might recall, it was just 1 dy, or 1 times dy. There was no extra y there. In this example, we have an extra y, so it's a little bit more complicated than that. Anyway, that's that example. I think this is the last sort of abstract one and not attached to anything. After this, we'll have some that are application problems. And there'll be, I think, 2 of those. Okay, so this is our first example of an application problem using a differential equation. So this problem says the net value of a small retail store is $20,000 initially and grows at 5% annually. Find the net value as a function of time. Okay, so these can be rather challenging because the setup is something you have to figure out. I think in the online homework, either the problem will be very similar to this, you can kind of model it after this, or you'll be given the initial setup differential equation. It depends on the problem. Anyway, so this part's just sort of window dressing, the net value, the small retail store, whatever. We have 20,000. So this is our initial value. It says initially, which is convenient. And in fact, well, you know what? The term value is important. And the value grows at 5% annually. Okay, so what is the value as a function of time? Well, it's going to be 5% of whatever it was previously, right? So the growth in the value will be 5% of the value. Well, 5% of means 5% times, typically, in word problems. So this means we're going to have 0.05 times, it's 5%, v, the value, okay? So 5% of the value will be the rate. So if the value starts out at 20,000, right? What's 5% of that? Is that 1,000 or is that 100? It's 5%. It's 100. Yeah. Now I'm worried. It's 1,000. Sorry, that's 1,000. You can check that on a calculator if you want to. 5%. Oh, it's 1/20th. Yeah, 5% is 1/20th, of course. So that means that initially the growth rate for the first year will be 1,000. If you were to do this like on a spreadsheet, you go, oh, it's 1,000, right? And then the value for the next year will be 21,000. What's 5% of that? Right? And then what's 5% of that? And what's 5% of that? And you would accumulate as you went along. So if this is sort of a discrete growth thing, like it's being compounded monthly or annually, right? If this is being compounded annually, you just use a spreadsheet. But we want a growth function. We want something that just predicts as far in the future, what's the value going to be 10 years from now or whatever. We don't want to have to make a big table. We want to just make a formula, right? So this describes that rate of change. If you plug in 20,000, you'll get 1,000. It will be the initial value for dv dt. Okay, so dv dt evaluated at 0 would be 1,000. So now what we can do is solve this differential equation using the techniques we did in the other examples to get v as a function of t. So I'm going to treat this like a separable differential equation. I'm going to move dt, just throw it on the other side. Okay. I need to move the v, because that v shouldn't be with dt. It needs to be with dv. So I'm going to divide v on both sides. And this is going to start to look like one we've already done, which is why we did that example earlier. So when we got to this word problem, it was a little bit more manageable. So if you want to refer back to that example before watching the rest of this, it wouldn't hurt. It's the one where dy dx equals y. I think that's what it was. Anyway, so now I can integrate both sides because I've separated the variables. So this is going to be the natural logarithm of the absolute value of v. Okay, ln the absolute value of v equals. And you might be wondering, well, wait a minute. The value is the value of the company, right? Net value. Could net value be negative? Yeah, it sure could. But in this context, we're going to find out that it won't. You'll see what I mean. Okay, so on the right-hand side, well, what's the antiderivative of 0.05? Or I really should say what's an antiderivative, but let's say what's the general antiderivative? Well, that's going to be 0.05t. So 0.05t plus c, of course. So at this point, I can say, oh, well, I need to move this ln, and it's going to become an exponential base on the other side. So the absolute value of v is going to be e to the 0.05t plus c power, okay? And at this point, we want to think about our initial value. The initial value is 20,000. I don't have a whole bunch of zeros, so let's say that this value is in thousands. Just because I want to have fewer zeros. So that means that my initial value would be 0, 20. Okay. If I wanted to use 0, 20,000, I don't have to do this. I just would have bigger numbers floating around, and I just want to have smaller numbers. Okay. So that means that when v is 20, okay, that means that I don't need to worry about plus minus here. E to the 0.05 times 0 power plus c. So this is going to be 20. Am I running out of room? We might have to start a new column, but I'm doing okay. This equals e to the c. So that means moving the e back over, the natural logarithm of 20 is the value of c, if I want to do that. Or I can just say, well, e to the c is 20. Either one of these will work, depends on the approach I'm taking. So let's do this. I'm running out of vertical space there. So let's take this, move it back up here, and I'm going to drop, let's do this. I'm going to drop the absolute value because we know the value is going to be positive, because if we know that the value starts out at 20,000, and it only grows annually by 5%, it only grows, we're assuming it doesn't shrink. Well, how's it going to become negative if it never shrinks, right? That's an assumption we're making, which is something we'll talk about in the next example. So this is going to be v equals e 0.05 t plus c power. I'm going to do what we did in the previous example, not the one right before this, but the earlier one with a logarithm. And write this as e to the 0.05 t power times e to the c. I'm separating the two exponents because when you have a product of two exponentials, you add the exponents together if they're the same base. But you can also separate. If you have a sum in the exponent, you can separate it into two bases. Okay. Now I know what e to the c is. It's 20. Okay, so I'm just going to replace this e to the c with 20. So v equals e to the 0.05 t power times 20. And if I want, I can reorganize that and say v equals 20 times e to the 0.05 t power. Okay, so now this gives me the value as a function of time. So I can say, okay, well, what's the value in 10 years? If I wanted to know that, okay, well, v, 10 plugged in, I guess I could be writing this as v of t all along, but we don't have to. It's 20 times e to the 0.05 times 10 power. Okay, so this will be 20 e to the 0.05 5 power, which is approximately, let me find a calculator here, 20 times e to the 0.5 power, I get 32.974. And I ran into 3 decimal places because my variable for value was in thousands. So this is thousands of dollars. So this corresponds to $32,974. Okay, and of course, this is assuming, it's making significant assumptions. This is assuming every year 5% growth, not 4.5, not 5.5, but 5% per year consistently. Not totally realistic, but it's a way to predict what's going to happen in the future. If you say, well, it's going to be something like 5%, between 4 and 6 somewhere on average, you would say, well, I'm making a prediction, right? Anyway, so the point is we were able to take a description of the behavior of a function over on a year-to-year basis, like what's happening, what's the initial value, what's the value of the company at the beginning, and then what's the growth like year to year. We can turn that into a differential equation, and then turn that differential equation into a function that will tell us, well, some point in the future, what is the growth? I mean, not the growth, sorry, but what is the value going to be? 10 years, 20 years, 30 years. One of the problems with this, and there's 2 problems, but one of the problems is the following. The graph of something like this, sorry, we're getting to the next example. The graph of something like this, well, the function assumes continuing growth forever. It doesn't slow down, which is probably not how a small retail business is going to work. Did I say it was retail? Yeah, small retail store. It's not going to grow forever. Say you're in a town with a certain number of people. If you only have, say, 8,000 people in your town and you're running a hardware store, and maybe the town surrounding, maybe you have the best selection or whatever, so people drive to your store. You're not going to pull 1,000,000 people because those people live, those 900,000 people that would make up your million, they live in a bigger city with like a dozen hardware stores, right? It's unlikely they're going to drive to your hardware store. So you might have a maximum. Like there's no way I'm going to be able to get above whatever it is, right? So that's what the next example we'll talk about, where we deal with some of the assumptions and limitations of some of these differential equations. Okay, so this is another application problem involving differential equations. It's somewhat similar to the one we just did, where we talked about the net value of a small retail business. This one, you could pretend is the same business if you want, just with a more realistic model. So the problem with the previous one is it assumed uninhibited 5% growth forever, which is just not going to happen, right? You're going to top out somewhere. Or realistically, you might, flag a little bit at some point. So let's say that we start out initially with $40,000 of sales for the first year, and we have a predicted maximum of $20,000. Maybe the business is in an area that's not very population dense, or it's just sort of remote from another population dense area. Maybe you're near a larger city, with 500,000 people, but there's a bunch. Say you have a hardware store, right? Well, in that bigger city, there's like a dozen hardware stores. People aren't going to drive to get to yours necessarily. So you're dealing with people in the local area. Let's say maybe you have like a potential of 10,000 people who might come to your hardware store, right, to buy what they need, hardware wise. So let's say that growth per year is 5% of the remaining potential in your maximum. So, there's people who've never heard of your store, or they've driven by and didn't go in or whatever. But through advertising or word of mouth or whatever, you kind of win them over and you grow your business by getting more people to come to your store. And every year you're whittling away at that remaining potential that you could get, just haven't yet, right? And so you're growing every year based on that. So we're going to find the annual sales as a function of time. So one way to do that would be to say, okay, we're going to have 5% of the remaining possible revenue. Well, R is going to be in thousands. So this could be 200 minus R is one way to do it. Because then if R is 200, you'd have 200 minus 200 would be 0. So your growth rate would be 0 once you get to the maximum of 200, right? So that kind of makes sense. But this actually is going to result in numbers that are kind of skewed. So what we need to do instead, and without going into why, we need a slightly different function that will basically just work better. I want 1 minus R over 200. And this gets the job done. It's essentially It's sort of like I just divided out 200 because the 200 makes the numbers too big. It's sort of like I just divided it out, but let's not worry too much about why. We don't need that much detail. So this function is going to model pretty well the growth rate. If I have sales of 200, if R is 200, well, 200 over 200 is 1. 1 minus 1 is 0. So 0 times 5% would be 0. So I would have 0 growth. I've reached my maximum, right? If my initial year I'm at 40,000, well, if R is 40, it's 40 over 200. That's 1 out of 5, right? So I'd have 0.8, and 5% of 0.8 in thousands would be however much that growth rate for that year would be, right? You just plug in that number of your current sales. That'll give you the growth rate for the next year, basically. Instead of making like a table in Excel or something, we're gonna solve the differential equation. So I need to do a couple of things. One way to get started is to go ahead and multiply the, well, let's do this. Our initial thing we always do is move the dt. I was going to deal with the 200 first. Let's not do that just yet. Let's just move the dt. So dr equals 0.05 times 1 minus r over 200 times dt. Okay, so we always start by just moving the independent variable, the differential of the independent variable. Now, remember, our goal is to separate the variables, get all the r's on one side and all the t's on one side, or the other side rather. There's only one t, so it's where it needs to be. Sorry, wrong tool there. There's only one t, so it's already where it needs to be. But this r has to move. So how do we do that? So we have to do some algebra to get going with this before we can do the antiderivatives. So I think what will be easiest is to multiply 200 on both sides. And you'll hopefully see what I mean by that in a second. So if I multiply 200 on both sides, 200 dr equals 200, and I'm going to go through all the details because I don't want you to get lost in the algebra because we're shuffling symbols around a little bit, and I don't want you to sort of tune out for part of it and not have no idea what's happening. So I'm going to show all the details, which might be a little bit tedious, but I don't want to skip anything. Instead of multiplying these two guys to get, like, what would that be, 10? I'm instead going to take the 200 and distribute it to these two guys. And I'm doing that to get rid of the fraction because I'm trying to clean things up a little bit. I don't want to have fractions if I can avoid them. I might get stuck with some, but I don't want to have fractions on top of fractions and fractions inside of fractions. So this will give me the 200 minus r that I kind of suggested earlier. It shows up again, but this is the approach to get it. So I'm going to have, on the left will stay the same. On the right, I'll have 0.05 times 200 minus r times dt. So 200 dr equals 0.05 times 200 minus r dt. Okay. So no fractions. Now I can divide both sides by 200 minus r to move to the other side. So I'm going to have 200 over 200 minus r equals 0.05 dt. Okay. Let's center this a little bit better. Okay. So I do get, oh, I forgot something. On the left, I forgot the dr. Maybe that's why I was off center. Okay, so on the left, I do get stuck with a fraction, unfortunately. So, but now I have r's on one side, t on the other, so I'm ready to integrate. And the way I do this, I have some options as to how I want to do this. You might notice the right-hand side is going to be easy. The left-hand side, though, I don't have to use a change of variable, but it might be easier to do. To see what to do with this. So I'm going to say that 200 minus r, let's pick a different variable. Let's go with v. V equals 200 minus r. So dv equals negative dr. Okay. So that means I can move this 200 out in front. It's just sort of in the way. Put it out there. And I'm going to need a minus sign. So I have to borrow a minus sign and put in the integrand. So 200 times the integral of 1 over 200 minus r, we haven't made the change yet, times, well, instead of dr, I'm going to write negative dr, because that's what I need to have according to this. So I have to compensate for this by putting a minus out here in front of the 200, okay? So that the left-hand side hasn't really changed. I've merely rearranged things. All of this here is the same as this guy here. I've put a double negative extra, but a double negative is, cancels, so I have the same thing. The right-hand side, I'll go ahead and leave as is. Well, yeah, let's go ahead and do this. 0.05 t plus c, as with the other examples. The left-hand side is the hard part. So now on the left-hand side, I can change over to the other variable, v, so negative 200 integral 1 over v dv equals 0.05 t plus c, all right? So I can, at this point, if I want, I can divide by the negative 200 now. I guess I could do it later. It's really optional. No, you know what? Let's leave it. Let's leave it how it is. Okay, so negative 200 times ln of the absolute value of v, right, equals 0.05 t plus c. Now, we have to think about v, not for value, just I picked a letter variable, is 200 minus r. Now, r is the revenue. Remember, 200 is the cap. 200 is the maximum. So v can't be negative anyway. How would it be negative since r is between 0 and 200, right? I mean, the revenue maximum is 200. So v can't be negative. I don't really need it. So negative 200 times ln of v equals 1 over 20 t plus c. So now I can divide by negative 200. So ln v equals, and this is a little bit messy, but we'll clean it up at some point. 200, okay? Okay, so now what I'm going to do is clean this up a little bit. I'm going to do two things at once. First, I'm going to replace v, because remember v is a variable that we made up to help solve the problem. So this is 200 minus r. I'm also going to divide this 200 into the two terms on top. So ln of 200 minus r equals negative 1 over 4,000. 200 times 20 is 4,000, right? Times t plus c. You might think, well, wait, hold on a second. Where'd the 200 go? How's this plus c by itself? Well, if you take some unknown constant that you don't know what it is, you divide by 200, you get some other unknown constant. So we don't really need to keep track of the 200. It'll wash out anyway. Now, this c is not the same as this c. They are different. So maybe I should call this one c2, just to distinguish it, okay? So we want to get r by itself. So I'll move the ln. So this is 200 minus r equals e. And I'll go ahead and turn this into a decimal. Negative 0.00025t plus c2. I'll add r to both sides. Well, let's subtract 200 on both sides. Let's do it in that order. There's lots of ways to do this. In the order in which we do it doesn't really matter. Negative 0.00025t c2. And then I'll multiply both sides by negative 1. So I get r equals 200 minus e, the negative 0.00025t plus c2 power. Okay, and what I can do is write this second term here by separating the exponents into two factors rather. So 200 minus e to the negative 0.00025t power times e to the c2 power. This is some constant we don't know yet. We're almost done here. I need to go back to that initial value, the initial revenue. The initial revenue was $40,000. And I mentioned but didn't mark that this is in thousands of US dollars. Right? The R variable is in thousands already. So 40 is the R value when t is 0. So really, this is like saying 0, 40 is my initial value. Okay, so down here, R is 40 when t is 0. Okay, so e to the 0 is 1, so I can subtract 200 on both sides. I'm doing this maybe a little bit out of order. Maybe I should have done it up here, but whatever. That's fine. The order in which you do these things doesn't matter too much. Minus e to the c2 power. So that means 160 is e to the c2 power. So that means this factor here is 160. So my actual revenue function, R, equals 200 minus e to the negative 0.00025 t power times 160. And if I want, I can reorganize that a little bit and say 200 minus 160 e to the negative 0.00025 t power. So that is my revenue function, the function of time. So I could say, okay, what's the revenue at 10 years? What is R of 10? Right? We did this with the previous example. It was something like 33,000, I believe. What does this one say? Well, 200 minus 160 e to the negative 0.00025 times 10 power. How much is that? Let me grab a calculator. It's not going to be a whole lot, but we'll see. So 200 minus 160 times e to the negative 0.0025 power. And I get, oh, it's more actually, 40.40. So that corresponds to 40,400. So yeah, that predicts more revenue at the 10-year mark than the previous model. What's the difference? Well, the previous model, if we scroll up and look at it, this previous model assumes uninhibited growth forever, which is not realistic. What does this one predict? Well, this one predicts something like this. There's a cap indicated like this, like an asymptote. So this predicts something like that. You're approaching that maximum, and you have very quick exponential growth at the beginning, and then it slows down as you approach. So this one assumes very quick growth. It also assumes, if we're starting here at 40, this model assumes, getting into the next example there, the model assumes that if you start out at 0, you grow faster at the beginning and you still end up there, which is not necessarily realistic. If your sales are a flat 0, this model says actually you'll grow faster at the beginning because your sales are less. But, word of mouth is people who bought your product and they like it, right? So, or they like the service or the prices or whatever it is. So having a lower initial value, realistically, maybe it shouldn't make you grow faster at the beginning. It should take longer to get ramped up, shouldn't it? So there's some limitations. This model assumes if you have no sales, they jump up quickly at the beginning. Not really necessarily realistic. So what would it look like if you had something a little bit more realistic? So in this video, we'll talk about extending the previous examples and the limitations they had and how to deal with them. We won't work out the entire thing, primarily because this model requires an antiderivative technique that we haven't covered. So we don't have to work out the whole thing. The examples we did are sufficient. But I do want to talk about this other model. So there's something called the logistic growth model, and it basically incorporates the benefits or the pros of the other two models without the drawbacks. So the first model, the exponential model, assumed like this uninhibited exponential growth forever, which is just not realistic. That's not going to happen. The other model assumed that, well, we have this maximum, which I'll draw out an asymptote here. quick. And the model assumed that you're gonna have growth like this, where you exponentially grow towards the asymptote. So you have this maximum you never quite reach, but initially you have this really fast growth period, and then you taper off at the end. But this also assumes that if you start out with nothing, that you have a faster growth period at the beginning. Like it grows even more quickly at the beginning, right? Which doesn't make a whole lot of sense necessarily. I mean, maybe it depends on the context. What are you talking about? But in general, it doesn't. So what would be a model that both has slower growth at the beginning and then also has this asymptote? What would do that? Okay, so let's say that the growth is somehow 5% of something, right? So 5% of 1 minus r over, say, 200, that's the number we had for the maximum. That would incorporate, that there's a maximum. That gives you the asymptote. But we also want the horizontal to be an asymptote, so that instead of jumping up like this at the beginning, it curves upward at the beginning. See how this growth here is more shallow at the beginning? And that's going to happen with causing the horizontal axis to be an asymptote. So if I say, let's multiply by r, so that when r is 0, when the current revenue is 0, the growth is 0. So if you've got no sales, you're kind of stuck there, which is not entirely realistic, but you'll see what I mean in a second. With the graph will make a little bit more sense. So what this assumes is if the revenue is currently 0, the growth will be 0, because when you plug 0 into this function, you get 0 growth. So 0 growth at 0 revenue. But it also assumes that when the revenue is 200, well, this factor will be 0. It will be 1 minus 1, which is 0. So you get 0 growth at your maximum as well. So the graph ends up looking like this. You have slow growth at the beginning. You have some quicker growth in the middle, and then the growth kind of tapers off at the end. That's not the best graph, but you get the idea. So this assumes slow growth at the beginning, intermediate to fast growth at the middle, and then tapering off growth at the end. Okay, this is much more realistic for a number of applications. I would imagine. Okay, so in say biology, if you track, say, the spread of an illness, as an example we can all relate to now, this is the model that tracks that. That's how it behaves. If you look at, say, the growth of a small business, that could. I'm not sure that the beginning is necessarily the most accurate. If you go take an advanced economics course, I'm sure they'll talk about which models best reflect, say, a small business, for example. But this kind of thing, the concept here is that you can build a model, a differential equation that models what you're describing, and the different factors, the 5%, the fact that you have a maximum, the fact that 0 revenue should result in 0 growth, that you can build in these different elements. You could say that my minimum is not 0. You could say, well, you know what? I don't want 0 revenue to be 0 growth. I want, if my revenue falls below a certain minimum, like what if my revenue falls below 1,000 per year? Well, then I'm just going to close up shop. There's no way to run the business. So you could do a different factor to incorporate that. And whatever factors you want to describe the different elements of what you think is going to happen, and you can solve that differential equation. You can get whatever model, and the graph will be whatever the graph is. It depends, right? But the idea is you can set up a differential equation that describes a real-world problem, solve the differential equation, and you get a function that describes the phenomenon without having to build the function piece by, just sort of by fiat. Oh, I know what the function is. You can build the equation and then find out what the function is. So it's a really powerful tool. Anyway, this is the last video in this short series. Just to wrap up, we did a few examples of just straightforward how do you solve a differential equation. Then we did a couple of application problems. And I just wanted to sort of extend the concept and say you really could do lots of different things with this concept.